Ever wonder how a computer actually thinks? Or how mathematicians can build entire universes of numbers from basically nothing? Well, it all boils down to a surprisingly simple idea: the rules for how we group things. Today, we're diving into set operations, which is kind of the hidden language that powers everything from your Google searches to the very foundations of logic itself.
So let's kick things off with a big question that sounds almost, philosophical. What could the absolute bedrock of mathematics and the super complex logic humming away inside a computer chip possibly have in common? The answer, as you're about to see, is actually beautiful, and it's the key to this entire explainer.
And there it is. They are both built on this one, single, powerful idea: the set. You know, a set is really just a collection of distinct things. When you look at these groups of numbers, integers, rational numbers, real numbers, each one of those is a set. It's just a clearly defined group. And this simple concept, it's the first, most essential building block for everything we're about to talk about.
All right, so let's zoom in and make sure we have a crystal clear understanding of these building blocks before we start, actually putting them together.
Okay, so here's the official definition. A set is a well-defined collection of distinct objects. Now, the two magic words here are well-defined, which just means we know exactly what's in or out, and distinct, which means each item only shows up once. So it could be a set of numbers, like 2, 4, 5, or it could be a set of colors, like red, green, blue. Pretty simple, right?
But, just having building blocks isn't really enough. We need a way to work with them. And that brings us to our toolbox. These are the fundamental operations we can use to combine, compare, and separate all these sets.
First up in the toolbox is the union, and it's represented by this U-looking symbol. The union of two sets is just everything that's in set A or set B or in both. That is the key word to remember for union, or. It's the most inclusive combination you can get. It's like when you go online and search for cats or dogs. You get all the results for cats and all the results for dogs. That's a union right there.
And this Venn diagram shows it perfectly. The union of set A and set B is the entire shaded area. You just grab everything in A, everything in B, including that part where they overlap. It's the whole shebang.
So let's make this super concrete with some numbers. If our first set is 1, 2, 3, and our second one is 3, 4, 5, their union is 1, 2, 3, 4, 5. And here's something important. Notice how the number 3, which was in both of the original sets, is only listed one time in the final set. That's that distinct rule we talked about in action. No repeats.
Okay, next tool, the intersection. Now, the intersection of two sets has only the elements that are in both set A and set B. So if the magic word for union was or, the magic word for intersection is absolutely and. This is like searching for cats and dogs. You only get results that have both. It's all about finding what they have in common.
And the visual here is the perfect contrast to the union, right? For the intersection, we only shade that little bit in the middle where the two circles overlap. That little sliver is the sweet spot. It's only the elements that the two sets share.
So if we apply this to our same number example, what's the intersection of 1, 2, 3 and 3, 4, 5? Well, it's just the set with the number 3 in it. And why is that? Because 3 is the only element that exists in both of the original sets. It really is that simple.
So let's just put them side by side because this is the absolute core concept. Union is expansive, it's or, bringing everything together. Intersection is restrictive, it's and, finding only what's shared. Getting this difference is the key to pretty much everything else.
Our next tool lets us subtract things. It's called the difference. And just like it sounds, A minus B gives you the set of elements that are only in A and are not in B. You're basically starting with everything in set A and just carving out any part that also happens to be in set B.
And finally, we have the complement. Now this one's a little different. It all depends on this idea of a universal set, which is just a fancy way of saying everything we are currently considering. So, for example, if our universe is all whole numbers and set A is just the even numbers, then the complement of A would be all the odd numbers. It's just everything else that is not in your set.
Okay, so we've got our tools: union, intersection, difference, and complement. But here's the really cool part. These tools don't just work randomly. They follow a clear, consistent set of rules, kind of like a special kind of algebra. And it's these rules that make set theory so powerful and so predictable.
Whoa, okay, I know this table looks a little intense with all the symbols, but trust me, you already know these ideas from basic math. The commutative law,
that just says order doesn't matter. A union B is the same as B union A. The associative law says how you group things doesn't matter. And the distributive law, that just shows how these operations interact, just like multiplication and addition do. It's all about making a reliable system.
But there's one set of laws that's especially powerful, and they're named after a mathematician named Augustus de Morgan. One of his laws says this: the complement of the union of two sets is equal to the intersection of their individual complements. Yeah, I know, it sounds like a real mouthful, but let's break down what that actually means.
So here's what it means in practice. If you take the complement of a union, that little apostrophe there means complement, it's the exact same thing as taking the complement of each set by itself and then flipping the operation from a union to an intersection. That flip, that's the magic of De Morgan's law.
So we've defined sets, we've got our operations, and we've got the rules they have to follow. But why should any of us care? What is the real-world payoff for all this abstract stuff? This is the final, and I think the most important part of the story.
And here it is. This is the big connection. Set theory isn't just for math class, it is the language of formal logic. A union is just another way of saying logical or. An intersection is a logical and. This is the fundamental grammar that computers use to reason, to process information, and to make every single decision.
And that connection to logic? Well, it unlocks everything you see here. Those rules we just talked about, engineers use them, especially De Morgan's laws, to design the actual logic gates inside computer chips, which simplifies the circuits and makes our hardware cheaper and faster. At the same time, programmers are using these exact same rules to simplify and optimize their code, making sure the software you use every day runs correctly and efficiently.
So we end up right back where we started. These simple, almost elegant rules for just grouping things together are the shared foundation for both the most rigorous proofs in math and the code that's running on your device at this very moment. It really makes you wonder, what other incredibly complex systems out there are just hiding a few simple, powerful ideas